Most developers assume their database transactions are bulletproof, but partial failures destroy data integrity silently. When your system crashes mid-write, you lose everything. You need to master ACID, Atomicity, and guarantee your database never reaches a corrupted state. In this lesson, we explore the core concepts of atomicity and consistency in database management. Here, we see a representation of a database, holding individual pieces of data that work together as a cohesive system. Atomicity follows an all-or-nothing rule, much like a light switch that must be either fully on or fully off, never stuck in the middle. When we perform a transaction, we are essentially executing a sequence of operations that must all succeed together. These operations move into the database as a single unit to ensure the process is complete. To maintain integrity, every transaction must pass through a strict set of rules. When the data adheres to these guidelines, it transitions to a valid, healthy state. Consistency ensures that the database remains balanced at all times, satisfying every constraint applied to the data. By combining atomicity and consistency, we guarantee that our database always remains in a stable and reliable state for every user. Today, we are exploring the concepts of isolation and durability in database systems. Isolation ensures that multiple transactions can occur simultaneously without interfering with one another. Think of these separate operations as parallel flows that remain completely independent and free from outside influence. Once a transaction is finalized, durability ensures that the data is saved safely to the disk. A secure gate locks the information in place, guaranteeing that it remains preserved even if a system error occurs. You can visualize isolation as a private booth where tasks are performed in solitude, while durability acts like a steel wall that keeps your committed data permanent and unchangeable. Together, these properties are fundamental to maintaining total transaction integrity. In the two-phase commit protocol, a central coordinator communicates with distributed nodes to reach a consensus. However, if the coordinator fails during the process, it creates a significant blocking problem for the remaining participants. When the central point of failure is removed, the remaining nodes are left in a state of uncertainty, called the limbo state, where they cannot safely commit or abort the transaction. To solve this, the three-phase commit introduces a safety barrier by adding an extra communication step between nodes. By establishing a pre-commit state, nodes can coordinate their intentions more reliably. As the system processes the request, the nodes communicate across this additional layer to ensure consensus. If a node fails to receive a timely response, the system triggers a timeout and safely aborts the process to maintain data integrity. Through this structured approach, the final transaction is safely confirmed for all participants. Welcome to our lesson on the CAP theorem. This fundamental concept in distributed systems explores the trade-offs we must make when designing large networks. Notice how the triangle forms with its three corners, labeled C for consistency, A for availability, and P for partition tolerance. You can only choose two of these three core properties to prioritize at any given time. We can focus on consistency and availability, or perhaps availability and partition tolerance, or even consistency and partition tolerance. Now, imagine two server nodes attempting to communicate across a network. When that connection breaks, it creates a partition. This tells us that having full consistency, availability, and partition tolerance all at once is impossible. If the network splits and data becomes contradictory, the system might trigger an error because it cannot reconcile the differences. Alternatively, the system might accept the partition but provide stale data to the user. Ultimately, we can think of consistency as a result of balancing availability and partition tolerance. As this triangle demonstrates, designing for the web is always a game of trade-offs. Today, we are exploring the difference between strong and eventual consistency. In a system with strong consistency, every read operation is guaranteed to return the most recent write. This ensures that all components are perfectly synced. It behaves like a metronome, where every part of the system acts in perfect unison. Moving on to eventual consistency, we see that updates are not immediate. Because of network latency, different parts of the system might reflect different versions of data for a short time before they eventually synchronize. The read value is essentially the last write plus some delay. On this graph, strong consistency maintains a steady, direct relationship, while eventual consistency shows a curve where the system catches up over time. Ultimately, choosing between these models depends on your specific needs for speed and accuracy. To achieve quorum consistency, we rely on a distributed network of nodes. When we want to ensure data integrity, we follow the principle where the sum of read and write quorums must exceed the total number of nodes. By selecting a subset of these nodes for our operations, we guarantee that information remains consistent across the cluster. Next, we look at causality tracking to understand the order of events. We represent individual nodes as distinct points that communicate over time. As these nodes exchange messages, we track the history of updates using discrete version markers. This allows us to determine if one update occurred before another by comparing their vector clocks. By analyzing these timestamps, we can clearly see the progression of versions within the system. Sometimes, concurrent actions converge on a single state, which then branches out as the system processes new information. This helps us prevent conflicts and manage parallel updates efficiently. Ultimately, these mechanisms work in harmony to keep our distributed system unified and reliable. Today, we explore race conditions in computing. When multiple users interact with the same document, conflicts can arise. Imagine two users attempting to access the same data file at the exact same time. Both users read the current state of the document simultaneously. User A attempts to write a change to the file. Then user B attempts to write a different change to the same file, effectively overwriting user A. Because both users performed a read and a write operation in parallel, the final result becomes inconsistent. One of those updates is now permanently gone. This is a classic lost update scenario. To prevent this, systems must implement proper concurrency control to manage access and protect our data. Welcome to our lesson on locking mechanisms in computing. Let us begin by visualizing how processes access data. Imagine a single resource, represented by this book. When multiple readers arrive, they can all access the data simultaneously. We use a shared lock, shown here in green, to allow multiple processes to perform read operations at the same time. This shared lock is essential for efficient reading. Now, consider a scenario requiring data modification. When a writer accesses the resource, we must use an exclusive lock, marked here in red. Notice that a second writer is blocked from accessing the resource, while the first holds the exclusive lock. This ensures data integrity by preventing simultaneous writes. We call this an exclusive lock, used specifically for write operations. By balancing these shared and exclusive locks, we achieve proper synchronization within a system, ensuring that data remains consistent regardless of how many processes interact with it. In computer science, a deadlock is a state where processes are unable to proceed because each is waiting for the other to release a resource. Imagine two cars approaching a narrow bridge from opposite sides. If both enter at once, neither can move forward. When processes attempt to access these resources, they often place a lock on them, preventing anyone else from moving. To visualize this dependency, we use a wait-for graph, where nodes represent processes and arrows show which process is waiting on another. A deadlock occurs when a circular wait is established, meaning every process in the chain is waiting for the next one, trapping them in an infinite cycle. One common strategy to break this loop is strict ordering, where resources are assigned a specific sequence that must be followed. By enforcing this hierarchy, you ensure that circular dependencies can never form in the first place. When managing these systems, engineers choose between detection, which identifies deadlocks after they happen, or prevention, which stops them from ever occurring. Database management systems rely on transactions to maintain integrity, but sometimes errors occur. Let us explore the three primary transaction anomalies. Here, we represent three concurrent transactions running in the system. When a transaction reads uncommitted data from another that is still in progress, we call this a dirty read. This can lead to serious errors as incorrect information propagates. Sometimes a transaction reads the same row twice and gets different results because another process deleted data in between. This is known as a non-repeatable read. Other times, a transaction reads a set of rows and suddenly finds a brand new item appeared that was not there before. This is called a phantom read. Protecting data consistency requires us to carefully manage these anomalies to ensure our records remain accurate and reliable. Welcome to our guide on SQL isolation levels. These settings determine how database transactions interact with each other. There are four main levels, represented here as read uncommitted, read committed, repeatable read, and serializable. We can see these levels range in strength from left to right. Think of isolation like a security gate. Transactions move from an open entry point toward a more secure environment. At the lowest level, read uncommitted, transactions pass through with almost no friction, prioritizing speed. In contrast, the serializable level locks data tightly inside a secure box, ensuring total consistency by isolating every transaction completely. As you increase the level of data integrity, you naturally see a decrease in overall system performance. This shows why database design is always a careful effort to balance performance and integrity. In this lesson, we will explore the core differences between pessimistic locking and multi-version concurrency control. First, consider a simple system where a reader accesses a book. When a user requests access, the system applies a lock, effectively making the resource unavailable to anyone else. Now, imagine a second reader attempting to access the same book. Because the resource is locked, a conflict occurs, and the second user is blocked from proceeding. To solve this, databases often use versioned snapshots. By creating copies of data, the system allows multiple transactions to view the information as it existed at a specific point in time. Each transaction accesses its own snapshot based on a unique identifier. This allows different users to work simultaneously without waiting for one another. Ultimately, pessimistic locking forces users to wait by blocking potential conflicts, while multi-version concurrency control enables smooth performance by maintaining multiple versions of the data. Today, we examine the persistence problem in computer architecture. At the heart of a system, data lives in two distinct places: fast RAM for immediate processing and the disk for long-term storage. Notice how data inside the RAM moves with incredible speed and agility. However, when we transfer that information to the disk, it must pass through a narrow funnel that causes a significant delay. This is why our total processing time is the sum of memory operations plus disk operations. The disk access time creates a massive bottleneck that slows down the entire system. Think of it like an hourglass, where high-speed data inputs arrive at the top, but are forced to drip slowly through the neck. As data piles up at this restricted point, we create a severe performance constraint known as the disk bottleneck. To overcome this limitation, we look to a better approach. The solution is batching. Welcome to our exploration of the write-ahead log, or append-only ledger. Here, we see the structure of a system consisting of a secure vault for long-term storage and a working notebook for immediate tasks. To maintain speed, we perform a sequential write. By writing entries one after another, the scribe ensures efficiency within the notebook. Once our work is recorded, it moves securely into the permanent vault. This process confirms that the write operation is essentially just a sequential append. Contrast this with random access, where data scatters across a system in an unpredictable and inefficient way. Instead, we use a structured, linear approach that maximizes performance. By keeping our operations organized in this clean fashion, we achieve high durability with minimal latency for every single transaction. The consensus problem is a fundamental challenge in distributed computing. Imagine a network of nodes that need to agree on a single shared state. In any real system, network failures are inevitable. Messages sent between nodes are frequently lost or delayed, which makes reaching an agreement difficult. To succeed, one node must distribute a value to all others in the network. This ensures that every participant is aligned and updated. The math behind this reliability is expressed by the formula n equals 2f plus 1, where n is the total number of nodes and f is the number of tolerated failures. Even when some components fail, the remaining active nodes continue to function to maintain system integrity. When these separate parts synchronize their information, they transform from a fragmented collection into a single unified and consistent state. Through this cooperation, consensus is achieved. The Paxos protocol is a fundamental algorithm used to achieve consensus in distributed systems. To understand how it works, we start with a proposer that needs to coordinate with a set of acceptors. In phase 1, the proposer sends a prepare request with a sequence number to the acceptors. Once the acceptors are prepared, they signal their readiness. Now we enter phase 2, where the proposer asks the acceptors to accept the proposal. When multiple proposers are active, the system must handle them by comparing sequence numbers. The proposer with the higher number wins the request and gains approval. This process relies on a core rule, where any new proposal must have a higher sequence number than the previous ones to ensure system integrity. This mechanism maintains safety by pulsing through the network to validate the state. By enforcing these rules, the system ensures that everyone eventually agrees on the same result, and consensus is achieved. Raft is a consensus algorithm used to manage distributed logs. In this system, one node acts as a leader while the others follow. To maintain this structure, the leader sends periodic heartbeats to all follower nodes to signal its availability. Once the followers are synced, the leader sends specific log instructions to ensure all nodes maintain the same data state. When a leader fails to send heartbeats, a term number comparison triggers an election. The nodes wait for an election timeout before initiating a new process. A new leader is then elected from the available candidates to take control. This process ensures a strong leader model for consistency across the network. Understanding asset integrity is essential for reliable distributed systems. A fundamental requirement is atomicity, where operations function as a single unit. When nodes must communicate, we can visualize this as data moving across a bridge between isolated systems. As traffic increases, this bridge faces immense strain, leading to performance bottlenecks and system fractures. We can summarize this relationship as consistency plus availability equals performance constraints. Latency is the primary factor here, defined by the sum of processing time and network delay. As we observe here, heavy network traffic creates expanding ripples of lag that directly impact the efficiency of your nodes. The two-phase commit protocol is a foundational method for ensuring consistency across distributed systems. It uses a central coordinator to manage communication between multiple participating nodes. During the first phase, known as voting, the coordinator asks all participants if they are prepared to proceed. Each node checks its status and signals its readiness by turning green. Once all participants have confirmed they are ready by displaying a checkmark, the system enters the second phase, called execution. The coordinator sends a command to all nodes to finalize the action simultaneously. As the nodes move in unison to complete their tasks, they ensure that the entire operation either succeeds or fails together. This process guarantees atomicity, which means your data remains consistent across the entire network, even during failures. However, this reliability comes with a notable trade-off. Because all nodes must wait for each other, the system can experience significant blocking latency. The two-phase commit problem creates significant challenges for large-scale distributed systems. When nodes fail or become unresponsive, the entire process can grind to a halt. To move beyond this, we turn to the consensus principle of majority rule. In this model, we do not require every participant to agree. Instead, we reach a quorum when a simple majority of nodes approves an action. This mathematical requirement, defined as half the total nodes plus 1, ensures that at least one node is shared between any two potential majorities. Think of it like a jury, where a clear majority delivers a final verdict, allowing the system to progress even if some members are absent. This approach provides superior reliability, as the quorum allows the cluster to function through partial failures. By maintaining active communication, the nodes continue to pulse with life, ensuring the system remains robust and resilient, despite individual node issues.